Thank you very much, John. And let me thank you as an organizer also, and Daniele, who is not around, who is the other main organizer as far as I understood. So I will talk about some work I've been doing with my PhD student, Adrien Lotti. But before to start, since the audience also include mathematician, let me just explain a few words about amplitude. So in some way, we say that string theory provides a theory of quantum gravity, and which is a big word, but for a practical purpose, what one can say at least is that string theory provides a way to scatter particles, which include a spin 2 massless particle, which will be the gravitons, and define in this way scattering, including Einstein theory of gravity. So here I define momenta as vector in the d-dimensional Minkowski spacetime. And for massless particle, one has a Minkowski signature scalar product which vanishes. And through this amplitude, what we mean is that we have a transition amplitude which define a distribution in that space, which involves some polarizations that I will not define, which I write schematically as T8, T8R to the 4. And assuming already without saying it that I have maximal supersymmetry, I can write the full set of amplitude for 4 particles. 2 particles gives 2 particles in terms of a single scalar function, which depend of my Mandelstam variable, Sij, and some moduli. So Sij find the scalar product between my external momenta, and where I use S equal S12, T equal S14, and U equal S13, as usual by in the way Mandelstam define. So the amplitude is defined mathematically in the domain of absolute convergence, where all the Sij are negative in the first place. But one needs to reach the domain, the physical domain, which will correspond to take the limit where S goes to R plus I0 plus. And what I mean by phi are expectation value of scalar field, so VEV, which semi-classically one can think also simply as a value at when reach the boundary at infinity. So string theory provides a way to compute this transition amplitude through perturbation theory. And the way it works with perturbation theory is that A of this Sij and phi is defined in string frame at least in terms of the expectation value of the dilaton as an expansion in genus, which I call H, greater than 1. So there is this exponential, expansion in exponential 2 phi, and where I have, so H loop amplitude. And then I only depend on other moduli, which I will not define explicitly here, G and B. So this genus amplitude can be written in terms of CFT correlators, which involve at 3 levels just the sphere diagram, then the torus, and then genus 2, etc., etc. However, this is expected to be a divergent theory, just like in quantum field theory in general. And I'm saying that mostly to make link with the workshop, whereas I will not really talk about this, but this is expected to be an asymptotic series. And so the full series should have Stokes lines, which will include not only so H greater than 1, but also some higher correction associated to de Broglie charge, where now we will have a double expansion in exponential 2h phi, but also exponentially suppressed term, which involve exponential minus phi and the D-brane Euclidean action. There is very little known about the resurgent property of the series, mainly because we only control the expansion at very low order in the genus. However, there is something that is very well controlled, is the low energy expansion. So when all the Mandelstam variables are very small in some scale, and usually one mean alpha prime Sij, where alpha prime is the string length square. And in this expansion, one can rewrite the entire function in terms of explicit function of the moduli phi, as well as supergravity amplitude. So what I can write in that case, let's say, is that A of Sij start with the three-level amplitude, which can be computed in classical gravity. I write a Planck length L just to decompose in low energy. There is a first function, which I call E0 of the moduli. And depending of the dimension of space-time, I have LD minus 2, which involve a Feynman integral, one loop of S and T plus cyclic permutation. I will just write the first few terms. There is a next correction, which is well controlled also. Phi, and then two loop, etc. So let me say simply that at higher order, this is what one could compute just within supergravity. So it's a supergravity amplitude, just a field theory amplitude with only massless state. This is identical at two loop. But at higher order, one needs to include also Wilsonian insertion of the string theory coupling, which appear here as function. So the first one that would appear would be LD plus 4 and include a one loop massive triangular diagram plus permutation also, which will multiply the first function, which is here. And it goes on for all order. So what we do control is that this function and this function can be computed exactly using bootstrapping method, using supersymmetry and U-duality. And those functions can be computed directly with supergravity or within string theory by expanding at low energy. So one question one may wonder then about quantum gravity is that how much quantum gravity is actually a string theory. And for instance, if you admit that you have maximal supersymmetry, as I'm admitting secretly in this case, which is supposed to be the simplest possible quantum field theory of gravity, is it true that type 2 string theory is a unique answer? And one way to try to answer that question is to wonder if the function that one obtained here are the unique functions that are consistent with the axiom one may require to be true in a quantum field theory. So this is a question that was raised by Vieira, Penedones, and Guerrieri recently, using the S-matrix bootstrap. And for this, we need to analyze the function which appear in the coupling, which is what we've been doing with my student, Adrien Lotti. So I will review a little bit this approach now. But before to do that, let me say that if I admit the maximally supersymmetric situation, the scalar field phi live in some specific space. So we have seen already last week several times, I think, that in type 2b, there is just a complex moduli which can be written as a Raman field plus the string coupling, and which parameterize the symmetric space SL2 by SL2Z SO2. And there is a generalization of this in lower dimensions. So if I will avoid d equal 9 because it's not pretty. So if I go to d equal 8, I have SL2 times SL3. In d equals 7, I will have SL5. And in d equals 6, I have SO55. And then I will have exceptional group, but I will not mention them today. Okay. So from just the point of view of quantum field theory, the transition function written here determines the S matrix. S matrix, which is meant to be unitary, at least in D greater or equal to 5, meaning D strictly greater than 4, strictly speaking. So because of this, the function Sij, where now I consider phi as being constant, which can take arbitrary value, is analytic on a certain domain that exclude S and T being in R+. And even if it's not proved in full generality, one may assume that it is actually analytic in all the complex plane minus those, the 3 copy of complex plane minus the 3R+, knowing that S plus T plus U is equal to 0, so there is some intersection because of that. This is sometimes referred to as maximal analyticity hypothesis. What is wrong, so the quantum theory should be unitary. However, in 4 dimension, when you scatter particle with momenta k1 and k2, you cannot differentiate them for infrared soft particles. And because of that, you have logarithmic divergences in the low energy for the soft particles. And you cannot make sense of a process like 2 to 2 or 2 to n. You have to be inclusive. So you should have observable, but you don't have an S matrix, strictly speaking, which is Lorentz invariant and Poincare invariant. Because any form of dressing with respect to all the soft states that you have to include to be inclusive enough to have a finite amplitude somehow will break your Lorentz invariance. But sometimes it's understood physically and there is no problem in principle. However, to use any type of axiomatic using the S matrix is really complicated and nobody, I think, has a clue of how to deal with this. Okay, but thank you because I think I'm usually too fast, so I'm glad that you asked questions. So, there is a condition of analyticity and there is a condition of unitarity, which just says that the S matrix is going to be a unitary operator. And so which means it's usually written that the imaginary part of T is just T dagger, which just means that if I sum over all the intermediate spin and intermediate momenta of T222 dagger, I should reproduce the imaginary part, but this, for this, I should also include all the n greater than 3 particles. With 2 to n and n to 2 process, which is written sometimes diagrammatically as a cut, where here I could have as many particles as I want inside. Okay, and a nice way to write this condition has been proposed in terms of partial waves, which is just a way to write the scalar amplitude A that I have written before in the form of a non-that, which takes this form. The factor in front is probably not so important, but the idea is to diagonalize the process. So you imagine that you have a 1 particle coming, another particle coming in the center of mass frame. And then they go out in this way. So you can decompose all the process in terms of the angular momentum associated to the scattering angle. And in this form, you just have a sum over all the angular momentum, which takes value as twice integer. And then the only dependence in S appear explicitly through an S function, which is a complex function here. And depending of the dimension, you decompose your angular momentum decomposition as a Gegenbauer polynomial in the cosinus of the scattering angle, which can be written as 1 plus 2t over S. And so in that case, unitarity simply tells you that in this diagonalized form, the complex function SL of S for any L and S has to be less than 1. And in particular, if you can neglect this part, which corresponds to more than 2 particle scattering, you would have, for the so-called elastic scattering, that SL of S would be strictly equal to 1 for all S and all L. However, one has to distinguish the two sets. I mean, this is meant to be analytic on the convergence domain, which means that the imaginary value of S is greater than 0, typically here. Whereas this is only true on the physical domain, where S is belongs to R plus I 0 plus. Just because there is a branch cut, it has to be on the right side. So to analyze this property, Polosh, Penedones, Toledo, and Van Rees have proposed to use the parametrization of the full amplitude using variable rho s, which simply map the convergence domain to a unit disk. So you just map C minus R plus to the unit disk. Of course, it's not the unique function that would do it, and one may argue if this is the best one, but this is the one they used. And so in this map, if I write the branch cut from S equals 0 to infinity, I can find that rho s is just mapping this domain to the unit disk with rho s equal 1 at the origin and rho s equal minus 1 at the end of the branch cut and all the way to infinity. And so if you want a function that will be analytic on all the maximal analyticity domain, you can just write an asymptotic series. A as the tree-level amplitude, and then a sum simply over 3 integer of coefficient depending of those integer of rho s and 1, rho t and 2, rho u and 3. So just because it's analytic on the unit disk, right, you just need to have a convergent theory here, which will have a singularity at the model of rho s equal 1. So just for condition at infinity, they also include the product of the rho e plus 1 square, but that does not matter so much. It's just to make the ansatz more regular at infinity. So in this form, in principle, you can parameterize any analytic function on the convergence domain, which will have nice branch cut, which this is why they use square root of minus s here when you reach the physical domain. But to use that for numerics, they want to truncate. And when you truncate, you lose the property, since you have a polynomial, you lose the property that you get the non-analytic piece in the physical domain. So one way to truncate consistently is to write an approximation, AKN, where instead of just writing the tree level in the first piece, you write what you know from perturbation theory, meaning the amplitude up to all loop less than k, which will be a non-analytic function to start with. And then you add this piece that I was just writing here, with now a truncated sum where each ni is less than a capital N. So they write this and that, and then they can demand by writing a transform to the partial wave formula, that this gives rise to a unitary process for all S below some, all L, sorry, below some N tilde bound, which is different from the bound N on the truncation. But if you extremize the bound, of course, what you get is an elastic scattering, which is not meant to be valid at all high energy, because it's clear that at some energy, physically one expects the scattering to be highly non-elastic, because you will produce a lot of stuff, including black hole, etc. But at low energy, it gives an excellent approximation, even if the ansatz is supposed to interpolate up to very high energy. And so if you take the solution that is critical, you not only obtain a bound on the low energy coefficient, but in principle, you propose also a numerical function for the entire amplitude, even if this amplitude is expected to be wrong at sufficiently large energy, where the scattering will be very non-elastic. So they have started this program, but in a very strong truncation. So where they consider k equals 0, meaning tree level. And within this form, they could compute a bound on the coefficients that are in principle known in d equal 10. I just give the numerical value and so they obtain in that case that the coefficient I was writing before, which were the coefficient in front of the r to the 4, the first Wilson coefficient you can have in d equal 10, is actually bounded by those values. But I now realize that I should not have erased one formula that I have to rewrite, which is the expansion of the amplitude A. So what is important here is the comparison with the one loop that you have. So you see from this comparison of scale that the first Wilson coefficient is only dominant with respect to the one loop correction if d is strictly greater than 8. And this is why in this case they only computed the case d equal 9, d equal 10, because it's clear that you cannot neglect I4 in this formula, for instance, if you want to go below d equal 9. But not only this is just a number, but the scale is out of the function. It's just a number, yes. So if you think of E00, I will come to that very quickly, but just to answer you now, if you think of E00 in type 2b as being a function of the S modulus, what it's meant to mean is that if you set the value of S such that the function E00 is minimum, this minimum is expected to match this value. But so it's not telling you something about the full function, just about the minimum. It's a number. E00 in string theory is a function. The bound they get from unitarity is a number. But consistency just requires it to be bigger. But if string theory is a unique thing that makes sense, you expect that it will be reached. Fair enough, yeah. I agree with you. Yeah. Yeah. Yeah, well, if they were getting something bigger, I would say clearly they do something wrong because I believe in what we are doing in string theory. But, so it's not, so I don't consider that as a check of string theory, if you want. But it's more like if they get a bound which reaches exactly what one has in string theory, I would expect this to mean that the corner of U-duality that I will mention briefly soon correspond to a saturation of the S-matrix bootstrap. And so that we can learn something from the S-matrix bootstrap about that point in moduli space. Yeah, I'm going to come to that, yes. Yeah. Yeah. The number from that is that you parameterize the amplitude in this way, so you have a very large number of Cn coefficients. But when you plug the condition of all the SL of S being infinite, you have infinitely many conditions to be reached. So what they do is that they check that for many value of S, and all the value of L that are below some bound N. So with all those constraints, if you saturate it, you actually fix the Cn. And once you have the Cn, you can read what is the minimal value of E00. No, but by k equal to 0, I mean the approximation setup. So here, this and that is meant to be fully general and to capture any amplitude. However, to get the non-analyticity of the amplitude, you need to have a sum which goes all the way to infinity. And what you can do instead, because numerically you'd need an approximation, is to truncate the sum of the coefficient of the rho s, rho t, rho u. However, to circumvent the fact that you are doing something wrong about your logs and all the non-analytic structure, you can repair that at low energy by including loop. But a less good approximation consists in, well, the more loop you include here, the better approximation you have, but it does not mean that you are fully wrong. And what they did is just to include only the tree level here. So it's not expected to be a great approximation, but it gives something sensible, at least in order of magnitude for those guys. Yes, but there is a difference between the loops that are included in this approximation. Here is some information. The fact that you don't include all loop here may be captured by your expansion in rho s, rho t, rho u, okay? Because at low enough energy, right, this series will capture all the behavior of your loop integral, and they will implement them numerically. It's just that the more knowledge you include about the low energy expansion, the better your approximation is, because you have an approximation scheme, right? If you put true knowledge in this, you will get a better approximation. We can, it's not clear, I see. No, because it's expected to be non-perturbative, I guess. Yeah, but yeah, indeed, yeah. If you want to write explicitly the one loop, you would need infinitely many coefficients here. So there is not a one-to-one correspondence between, because it's already non-analytic on the physical domain. So by definition, it includes an infinite series here. Yeah. So there is something I did not say here, however, is that you would still write them in terms of row variable, which would agree with that up to up to an approximation when you go at low energy. Because this is redundant information a priori, so you don't want this to kill the good approximation. Okay. So let me go back to this case. So here you see that below 8 dimension, you cannot really trust this term. And if you go even at higher order, you will have to include even higher loop correction. But let me just explain the E0, 0 and come to the trial function you were mentioning. So in case I have a chance to get them back, I can try to get the mathematician back, because now we'll talk about Eisenstein series, and it will be related to this, but does not require exactly that. So E00 is known to be E3 from Gutperl and Green, where ES is like the Eisenstein series, sum over M and N in Z, excluding 0, of, I will use this S2 notation, M plus NS to the 2S and to the power S. And so one may demand what is the minimum of that function in the first place. And this was... sorry, so let me change name if you are not happy. I will write U for the variable, and S is a complex parameter. So it's convergent for real S greater than 1, and U is equal to U1 plus I U2. Is it better? Sorry? Yeah. So U is C0 plus I exponential minus phi in this. And so Rankin has proved that the minimum of that function is at the corner of the moduli space. It has to be a special point, as one may expect, which is related as an image to the cubic root of unity. And for this, he used the explicit Fourier expansion of the function and not only the sum, obviously. And he's able to show that the only local minima are associated to symmetric points, so either I or this cubic root of unity. And moreover, this can be computed explicitly then, because one can recognize the corresponding sum then at this special point as corresponding to Eisenstein integers, which if I call this minus omega bar are defined as the integer m plus n omega. And so the value of ES is just related then at that point to the L function associated to the Eisenstein integer, which is the L function associated to the cubic root of 1 for the field extension. So the question we ask ourselves with Adrien is to generalize this to other Eisenstein series. So this has been also addressed by mathematicians for different reasons, because in the same way that this is associated to a field extension for a quadratic extension for rank 2 Eisenstein series, if you do higher rank Eisenstein series, this is meant also to count L function associated to field extension, but in a much more complicated way. That's right. So I should have said that. You get something which is slightly bigger, which is 8.89. In type 2A is slightly bigger because you don't have the non-perturbative expansion. I did not recall that one. Yeah, yeah. Yeah, so it's not that good. Actually, in the first paper, they had a better approximation. They were very happy. But then they have improved their own computation, and they find a bigger gap. Yeah. No, they should have. but however, the fact that they don't include the one loop, I mean, in D equal 10, the difference is not so big. So this is most probably not legitimate. So I would think the fact that they get that close with such a bad approximation scheme is a sign that there is something. Okay, so I want to generalize that now to higher rank Eisenstein series. So when they find ES in the same way for SLN as the sum over Zn, and I write a bilinear form H of this vector n to the power S. So it's exactly the same formula. This converge for real part of S being greater than n over 2, but there is an analytic continuation to the whole complex domain. There is only one pole in that case at S equal n over 2. And one can define, just like for Eisenstein series, there is a completed function, which is just defined as for the zeta function as pi minus s gamma s of ES SLN. And this function satisfies a functional identity n over 2 minus s of h is equal to ES at the inverse matrix H. So H and H inverse corresponding to a fundamental and anti-fundamental representation. So now one may wonder what are the minimum of that function. And at very large value, so I consider S in R. And at very large value of S, it was already analyzed by a mathematician. So if I have S much greater than 1, one can actually expand this function by corresponding, by taking all the vector n of minimal length. So in that case, it's easy to check that if I count the number of vector with a minimal length, which generically would be only one, but one may have more than one, then the leading coefficient in 1 over a power of s will just be the h for which the length is the smallest. And so then I will have correction which are higher inverse power of s. And so if one wants to consider which are the minimum of that function, well, this will correspond to the largest possible h. N-free bosons. Yeah, but I'm not sure I can talk about this without turning the field. And also here I'm only parameterizing. So SLN by SLN Z SON. What you are talking about is the subspace GLN inside SONN. But if I have time, I will go to SONN. Here, don't think about that. It's just the moduli space of the torus, TD, without the volume that you should think here. But so a nice parameterization of this object is to think of a lattice, and to think of a lattice when define H of n, the bilinear form, as a bilinear form which is not unimodular. to the power divided by its determinant. So it's a trivial fact. It's just a useful fact because then I can write in a corresponding lattice n in the n with bilinear form y of n. I can think of what is the density of packing, and I write rho of y as just the set of vector I can set in a sphere. So for this, I consider the sphere of radius square root of y min divided by 2, sorry, yeah, to have the distance. And I divide by the volume det of y. And I get that this function only depends on h, and therefore for h of m min being maximum, I will get the densest lattice packing. So the conclusion is that h is at the densest lattice packing for ES minimum. And those are classified in terms of Lie algebra. For n less than 8, as you might know, you get you can write them in terms of Cartan matrices of simple Lie algebra. Where you get all the way to E8. So the question one may wonder then is what happens when you go for small s, and actually in string theory, we'll need to go actually below the convergence range, where this argument does not apply at all. So in particular, we want to expand this result inside the what is called the critical strip, where the function is not convergent and neither is its functional image. So the argument to extend this is to look for points which have a chance to be critical points in the first place. So if I think of the simple example of SL2, which by the way indeed corresponds to A2, right, the hexagonal lattice, the way to generalize this notion is to define the notion of symmetric points. So if I take gamma inside SLNZ, I can define the image in moduli space phi gamma. And by definition of the fundamental domain, if I start from a point in the interior of the fundamental domain, I go out of the fundamental domain. But if for phi, which are in the boundary of the fundamental domain, just like it was the case for the spatial point of the cubic root of 1, I may have phi gamma equals phi, so stabilizer point. In 2 dimensions, any stabilizer gives an isolated point. But for SLN larger, we have more possibilities. However, we may look at isolated point by looking at the action of gamma on the tangent space of the fundamental domain at phi, and demand that this action does not have invariant vector. So in that case, the symmetric point is isolated, and we call them actually symmetric point. So for SL3, one can prove that they are the only extrema, and with some numerical check, which conjectures that they are the only extrema in general for SLN. But we don't have a full proof of this. So if you include this, then you can just classify possible extrema in terms of a symmetric subgroup of SLNZ and their corresponding bilinear form. So one subset of them correspond to the case where H is factorized, where X equal to 0. But in that case, actually using the expansion of the Eisenstein series, it's very easy to show that the second derivative of ES SLN at dx is like a sum of positive term. And therefore, any extrema that would correspond to a reducible matrix H has to be a saddle. And therefore, we concentrate on irreducible matrices. And for this, one can find a classification. So just for the case of interest, they are all Lie algebra lattices. But also, this is a very large dimensional space. So just to actually show that you have a minimum is not so easy. But what you get at those symmetric points is essentially that TF will decompose into a finite number of irreducible representation. And in particular, if I take H corresponding to H AN type Cartan lattice, you can simply check in that case that T F at this point decompose into only two vector spaces corresponding to representation of the Weil group. And in the same way, TF dn decompose into two representations of the Weil group. And so in this way, if you want to prove that there is a local minimum, you just need to compute two appropriate eigenvalue of the Jacobian. So it makes the proof very easy. One second property you have also is that each ES of SLN satisfied to a Laplace equation. So in the domain of convergence, this ensures that the sum of the eigenvalue of the Hessian are positive. But if you go below in the critical strip, you just get that the trace of the Hessian is going to be positive if and only if ES is negative. So in particular, a global minimum must correspond to, a local minimum must always correspond to a negative value, which from the amplitude may be a little bit counterintuitive because usually people expect the Wilsonian coefficient to be positive. But there is an explanation to that, which I will come back to soon. So the way you can prove actually this fact is that in the critical strip, n over 2, the function ES is actually L1. It's not L2 square integrable, but it is integrable. And by integration by part, you can show that the integral is 0. So you know that there must be a negative value, and in particular, the global minimum must be negative. And so with the two property, you obtain the two property are consistent. Yeah, sorry. But what is important for our check is that we could just check on the subsurface of two dimension inside F that the function is a local minimum. So just to give the example of SL5, all the symmetric points have been classified. So one gets the lattice and their dual, A5 star, A5 plus 2, and A5 plus 3, where those lattices just correspond to adding some root fundamental weight to the corresponding lattice. And where the symmetry group are just either W of A5 or W of D5. All of them correspond to local minima at large value of S, but only D5, which is the densest lattice packing, is a global minima at all value of S greater than n over 4. And so in that way, one can compute the minimum of the Eisenstein series that appear in string theory in D equal 7. So let me mention then some generalization. So if we go down in dimension, one may consider the next step, which is SO55, in which case you will get your favorite bosons in the torus. And so in that case, the function which appear is the minimal Eisenstein function. So one can define in a similar way the sum over all momenta in the Lorentzian lattice to an n which are 0. So we just correspond to the integral of an Eisenstein function on the Naryn lattice, where h of q is indeed defined in a similar way as g minus 1 of m plus bn plus g of n. But so if one takes the critical value, which corresponds to the integral of 1, this function simplified drastically. And correspond to what is known as a minimal Eisenstein series. And this function could be analyzed using a similar argument. So where one gets sorry, I'm not sure where I write that. So those four equations drastically vanish in this very case. And using the same argument by symmetric points, what one can get that the symmetric points that correspond in that appear in this case is where you have enhancement gauge symmetry in string theory, meaning that the lattice Pn can be decomposed for a given lattice as a sum over cosets of L plus mu, direct sum with L plus mu minus 1, where L will be again a Cartan type AN, DN or EN. Lattice at least for small size. So one way to intuitively understand this is that there is a very simple trivial example of this case, which is ES of SO11, in which case you would simply write 2 zeta of 2s, R of 2s plus 1 over R of 2s. And it's very simple to see that the minimum in that case would be at R equal 1. And the generalization of this, if you do it for ES SO33, is actually related up to a factor of pi to the series I was defining before. So this has to be for half, the value at 1 of SL4. And one finds consistently that the minima, that is D4, is indeed corresponding to the sum of the A3 plus mu, A3 plus mu. So let me just mention then to finish that there is a behavior which always appear. One can relate the coupling function to the non-analytic parts for which the first logarithmic divergence appear in supergravity. And the coupling function E00, 0, for example, is negative in D less than 8, not infinity, sorry, which correspond exactly to the critical dimension D equal 8 of the one loop divergence. When check exactly the same thing for the next coupling function being less than 0 correspond to D less than 7, where D equals 7 is a critical dimension, and the same holds for D less than 6. And that just follow from the property of being L1 or L1 of being L1 of the function, that the minimum has to correspond to a negative value. So even if there is dominant contribution which correspond, which appear before those functions, it seems that they are still tied to the corresponding logarithmic divergence in supergravity for the domain of positivity. There are a lot to be done on the S matrix bootstrap to generalize this. So one needs drastically to include loops in order to be able to test the relation with the SL5 function and to make the relation with the higher dimensional function in the equal 10 more accurate. And on the side of the minimum, we still have to go to a non-minimal series. For which it's pretty clear how to proceed. Actually, we have some in that the next to minimal behave in the same way. However, for E6 or even E7, it's not clear how to classify symmetric point, and we did not find much in the math literature about the corresponding classification. So we did not have really a good starting point to try to investigate those cases. Okay, thank you for your attention. So for D equals 7, they did not compute it, and I gave it for D equal 10. It's about a tenth, I think. And in 9 dimension, it's about the same. But in D equals 7, they did not compute. I mean, it would not make sense to do it with 3 level. The one loop is then dominant. So excluding it does not give a meaningful result from the point of view of the S matrix bootstrap. That's a good question. So if you don't consider the correction, for example, you would get that the minimum is at I for the fundamental domain. So what I'm saying, no, you want to go as down as possible. So you would get actually this value as well. But and so most of it actually comes from the perturbative term, even if you go down. But that's the case for the minimal. We did not investigate it in too close detail, but I believe that for the minimal, essentially the constant term is most of the contribution. You get the right order of magnitude. No, but I mean, obviously, by this I mean that you are in the right fundamental domain. If you go close to a rational, it's very wrong, obviously. But also to evaluate those numbers for the Eisenstein theory, we also evaluate numerically, and we use the Fourier expansion, and we use it in the correct fundamental domain, not in a crappy one. You want a convergent expansion in the Bessel function. I mean, very convergent. But essentially, the fundamental domain is such that the y are order 1, so the Bessel function are already pretty small. As long as S is sufficiently small, actually. So we describe that actually doing a generalization of something done by Grenier for the fundamental domain. Grenier is a mathematician who studies the fundamental domain of SLN. And so you can describe it. The thing is that it's not as unique as for SL2. But a nice parametrization is you take all the maximal parabolic. The thing is that are abelian. It's not necessarily unique, but you take a series of abelian parabolic included in one another, and each time you have a prescription for defining a fundamental domain out of them. So you just move through the hyperbolic space, and you check that your inversion is making the best for the measure, and so there is a definition that we give for that. And actually, one can check in each case. Yeah, I did not come to that. Thank you for the question. I was talking about U-duality corners, where one can check that in the fundamental domain, all the maxima which we find are always at strict corner of the fundamental domain. So codimension maximal intersections.